Oh, okay, I think I just answered my question. So the initial would be the disc and the final would be the stick.
In this case, yes.
Okay, so on this one, the initial would be the ring and the final would be, no,
Yes, so far, this is good.
that was right? Oh, the initial would be the ring and the final would be the disc.
Yes,
Okay, all right, I answered my question.
okay. However, I think there was some other question that was out there.
I'm just.
Okay, you want me to keep going?
Here for the
All right.
ride.
Let's assume that the length of this stick is the same as the radius of that. I have to give you some other piece of information, but, so, this formula right here, I don't know if this one's in your textbook, but if, on something like that, if, on a test or a quiz, I would give that to you. Or you would ask, if I forgot. So I would be 1/3 times, given the magical properties that I've done on this, that somehow it maintains the same mass, 2 times 3 squared, which would be 6 kilogram meter squared. Yeah. So by reconfiguring it, we've changed the moment of inertia. How easy is it to actually get this thing to spin? In this case right here, we went to a lower moment of inertia, which means we made it easier to spin. So therefore, it should spin faster because it's easier to do it. If I have this thing initially spinning at 7 radians per second, or 7 some unit of turning divided by time, some unit of time. So revolutions per minute would also work. Degrees per second would also work. Radians per second just happens to be the international standard. So I'd have 9 kilogram meter squared times 7 radians per second. And the claim is that that product there, when you multiply them together, the 56, is going to stay constant for this problem. That's the conservation law. And that's equal to 6 times whatever the final velocity is. So mathematically, I'll get 63 is equal to 6 omega. Omega final 10.5. And it would be the same units as the 7 was, radians per second.
But you were right, I was making it harder than I was.
Okay. I think that's physics in general.
Well, it's everything, it's fine.
I still think the biggest issue a lot of students have is trying to bring too much reality into it. Because I believe I specifically stated it magically changed in this problem.
Yeah, you did.
So when an object has less rotational inertia, it is easier to spin and easier to stop.
Yes.
So for 2, with the 2 marbles on the sandy hill,
Yep.
would it be marble B because it has more rotational inertia, so it's harder to start, but also harder to stop?
Right.
Okay.
But I have to do something with the sand too though, right?
Well, the sand's trying to,
Because if you have more rotational inertia, you can power through the sand.
yes,
Therefore, that's why it has an advantage.
yes,
Because the one with less rotational inertia is gonna have a hard time getting through the sand.
right. It'll start out faster, but the first obstacle that it hits, it's gonna stumble more than red number 3.
Oh, and
Or-
I didn't understand your video with the 2 tapes. You know what I'm talking about?
Yeah, the one in front of the computer, and you
Yeah.
got to see about this much of it?
Yeah.
Okay,
So, which one actually won? The smaller one?
I forget, that was the hoop and, which
Yes. Yes, you're talking, the
The-
hoop one, yeah.
hoop and disc?
Yeah.
Or- What are the chances I put my hands on exactly what I want?
because, no, they both had a hole in it.
Well, I mean,
That's
this is
why,
hoop and disc, these are actually manufactured and not stuff I just picked up.
cause that's why I was confused, cause like you used two, like, I get, they look like tape,
Yeah,
like rolls of tape.
I've got. Well, these aren't the same thing, but.
But then you said one had more and one had less rotational inertia, but they both had their mass on the outside.
So I was doing two discs.
Yes, I guess.
Okay. And there are lots of variations of this. I don't remember exactly what I did. I mean, here's two discs.
Yes, you had it like
Okay.
that. I just don't understand why they would have different rotational inertia.
Okay, looks like that's cool. All right, so it was something like this, it was the one where I had two hoops of different sizes?
Yeah.
Okay. This one has more mass than this one does. This also has a larger radius. More importantly, it's a larger radius. So, because in the formula, the radius is counted, has more impact than the mass does because it's squared. So the moment of inertia of this disk is more than this disk. Or sorry, not disk, hoop, of these hoops. So if I release it, they basically are staying together.
Yeah.
There was a slight difference there in the fact that this is slightly thicker than that is, and so there is a subtle difference there. But they basically stayed together. Because ultimately, it's the distribution of mass was the same.
Okay.
So therefore, they would get to the bottom, roughly at the same time.
Okay.
I think that's what I was
thought
going
that was the
for.
answer, but it was confusing, cause you were like, it's a little bit different, and I'm like, what? Why would it be different? But you said it might be because it's a little bit different.
Yeah, the thicknesses are slightly different, or that thickness is more of a percentage of the radius than that thickness is.
Gotcha.
Can we go over master set question 3?
What was 3?
I applied 10 Newton force to a lever at a point 3 meters away from the lever's fulcrum.
Okay.
There is not enough information to determine the magnitude of torque I applied in most situations. What information is missing to find the torque for most cases, and in what case is it possible to determine the magnitude of the torque?
Okay, so, let's take the example of the door. The door, we'll just say has a width of 1 meter. And I'm going to apply 5 newtons of force to it. What goes into finding torque anyway?
The lever arm and the force.
And,
Rotational.
The direction of the force.
so in the case of where I just said 5 newtons of force applied to 1 meter from the axis, that's as simple as I'm exerting no torque at all right now. Because how I apply the force matters. So that's why in that particular problem,
You need the angle of the force.
yeah.
And then for the
So lever arm would be wrong. I put lever arm and direction of force.
It depends on what you mean by lever arm. Direction of force. Yeah, what was the wording of the question again?
I just put lever arm because I knew it goes into finding torque. But I know definitely the direction of force is missing.
Yeah, direction of force is the main thing right there.
You guys an
So
angle of the
The
force?
trouble with lever arm is it's used slightly different ways, different times, and so it depends on what you meant by that.
I don't know.
The way, in physics 110, generally treat the lever arm as a vector from where the force is, from the pivot point to where the force is applied. So in that, if that's the case, then the
It would
lever arm is
tie in
3
to-
meters.
Okay,
So we know at least the length of the lever arm, it's the direction of the force is the main problem.
How would the ideal question be worded? Like, how would it be worded if it were perfect and gave us everything we needed to find torque?
Oh. It depends on how many words I want to throw in.
Okay.
When is, since I gave you the magnitude of the force and I gave you the magnitude of the lever arm, when will the torque just be those two things multiplied together?
When the angle's 90 degrees?
Yep.
So that would be the answer to the second question? Okay, I figured that the second one was just if we know the angle of the force applied period, cause can't you figure it
Yeah,
out from that
in
angle?
what
general,
about
yes.
the equilibrium?
Yeah, mechanical equilibrium, right?
Mm,
Equilibrium would mean there's
Meaning
no
it's like
acceleration.
this, meaning it's equal, like it's not leaning towards one way.
Yeah,
I just kinda saw
So
mechanical.
is it, for 3D, is the angle?
yeah, if you know that angle, you can find it, or if specifically, given, with the information given, you just said the force is applied perpendicular to the lever arm, then done.
If it was a right triangle, we could use Pythagorean theorem, would that be okay?
No, right triangle,
Or 90
yeah, right angle, if the angle between the force and the lever arm is 90 degrees or a right angle, I'm good with that, but you throw a right triangle in there and there's not enough information, because I can turn anything into a right triangle. Any vector into a right triangle. Not necessarily usefully, but I can do it.
So should we write about the 90 degrees or just if we know the angle of the force applied is fine?
I'll accept if you know the angle.
Okay. And how would you calculate it from an angle that's not 90 degrees?
You got some trick?
A little bit.
Okay. All right, this is a 15-second aside, this is beyond the scope of the course.
Tree. Look away.
The magnitude of the torque would be the magnitude of the lever arm and the magnitude of the force times the sine of the angle between them.
Okay.
That's how you do it. And back. If you've never had trig, don't worry about that. Or, obsess over it if you want to.
Or,
However you roll.
I still don't understand why it wouldn't be at equilibrium.
If I were talked about applying a force to an object,
Mhm.
if equilibrium were involved, see, it depends on what you mean by equilibrium.
Cause it says, in what case is it possible to determine the magnitude of the torque?
So you're saying if the object's in equilibrium?
Yeah.
Meaning that it's not accelerating, no angular acceleration?
Yeah, like it's not going, it's
Linearly
it's
or
not moving,
rotational?
it's not more on one side.
Wouldn't
Like,
it be-
I'm thinking of something like this,
Now, I can,
and this is.
Like the
torque.
seesaw
Yeah, like the seesaw.
in the book.
all right, so if you're doing that route, and so you got a fulcrum here and you've got,
Okay.
something balanced on top of it,
Yes,
and you're applying a force 3 meters from the pivot point,
yes,
so out here.
yes.
Equilibrium is lost unless you're throwing in.
Wow, yeah, no, I was stupid,
Okay.
okay, never mind.
But see, now it makes sense.
It does make sense. My bad.
Now, as a side note, you could probably work equilibrium into it, but that's a whole lot more trouble.
I'll word it wrong and I'll confuse myself.
Okay.
I mean, it would be if you just turned your head. I mean, it would work out.
Turn your head along with it.
Yeah.
That would be called a rotating reference frame. It does not change the torque acting on it, it just changes your perception.
You got an answer for everything, huh?
I mean, I'm trying here.
I wish I had an answer for everything.
It seems like it.
It's not like this is the first class to ask some of these questions.
That's
Actually, I think that's the first time that's come up, but,
Wow.
Hey, you're the first.
but I haven't been doing master sets for 110, until recently.
What would 110 get then?
Sorry?
What would 110 get then if they didn't get master sets?
More traditional, the master sets came about when I suddenly had to do 110 online and
I would-
couldn't do the traditional homework quiz. So, in a full face-to-face class, I have not done master sets. And we just did homework quizzes. For better or for worse.
It seems like you like master sets better now though.
There's something nice about looking at it where students have had a chance to think about it and, you know, get help if they need it, as opposed to the, all right, you've got 20 minutes to show if you can regurgitate what you saw in the book. All right, other questions right now?
Is 9 asking for a number? It is, okay.
Also, can I borrow a calculator and can you show me how to do those?
A planet with a mass half of Earth's mass and twice Earth's radius would have an escape speed. So that's a straight up, if you have the formula for escape speed.
It wasn't in the book.
No, it's not, but there are references, the hit document is now there.
I saw it.
So that should point to the video and the exact time where the escape formula is.
Okay.
I think it's square root of 2 times big G times the mass of the planet divided by the radius of the planet.
Yes.
Square root.
Wait, where did you just square root it?
I just Googled it. VE equals 2 big G and.
I don't think you told us to square root it the first
See
time.
what?
The formula I did on the board the other day was the radius of the black hole.
Equals square root of.
The formulas are actually very much related. That the escape speed, if that's the square root of 2G mass of planet or radius of planet. If I square both sides, I get V squared is equal to 2G over R.
Yeah.
And then swap those two across the diagonal, and I got the other formula.
Alright.
So, wait, the only letters that make a difference if they're big is just G, right? Big G and little g? But
Those
the
are
M
two
and the
different
R are
things.
just mass and radius.
Right,
Okay,
right.
just two.
Some textbooks do distinguish between little r and big R, as in big R would be the radius of the whole object, and little r is the distance from the center to some point within it. I play fast and loose with that convention. Noelia, is that your hand?
Yeah, I know you went over this on Tuesday, but for me, the coefficient of static friction between the road and the tires, I'm
Yes.
still confused on that.
Do you know what the centripetal force is? I think that was the answer to part C.
Yeah.
Well, you know, I'll make up numbers. So I have a road here that a car's going around. Radius of curvature of the road will make 200 meters. Car is cruising along at 20 meters per second. And we're just saying that's barely keeping it on the road. It's a little bit faster and it's gonna start to slide. So we're at that breaking point with static friction. We're talking nice and ideal that the car, there's a perfect roll on the wheels. So as it's going around a curve, from a back end view, there's my car. Force diagram of car, I've got weight going down, I have normal force going up, and there's friction acting towards the center. Friction is what keeps it from sliding. So that is the force that keeps it in the turn. The weight, let's make the car 1,000 kilograms. That's the mass. So the weight would be 9,800 newtons. Assuming it takes place on Earth. because the car is not accelerating up or down, the normal force would equal that. Vertical equilibrium. So this would be 9,800 newtons also. The friction, as my centripetal force, is gonna be equal to mv squared over r. And you have m, you have v, you have r. You plug and jump.
MV squared over R.
Yeah. And I think that's what you do for part C. So, let's see, that would be, I'm getting somewhere around 2,000 newtons. I think, if I did the math correctly in my head. So, the coefficient, if I'm at that breaking point between static and kinetic friction, in other words, the breaking point between when it's not sliding and when it does slide, then static friction equals, this is my maximum static friction, is equal to that coefficient times the normal force. If there's multiple normal forces in the problem, it's the normal force where that friction is occurring. That friction is occurring between tires and road, so I want the normal force between tires and road. There's only one normal force in this problem, so it's not tough to figure out which normal force you need. So in this case, that would be 2,000 is equal to mu s times 9,800. So 0.2 something,
How do you do that in your head?
Okay.
rounding.
I'm like a human, I can barely add 2 plus 2.
I just okay with my
So in elementary school, were you allowed to use calculators?
No.
Okay. Do
Are
they,
you?
no,
I barely use
I didn't
calculators.
I was, we got our first
Okay.
calculator when, the family got a calculator for dad to do taxes when I was in, I think, 5th grade.
Okay, well, I didn't wanna go there, but.
You could add, subtract, multiply, and divide.